Good morning, one and all. Today my topic is application of Biot Savart's law. And my name is Alampa. I am related to the aeronautical engineering. In my subject in aerodynamics, I am going to deal with the application of Biot Savart's law. First of all, about the Biot Savart's law. Biot Savart's law means Biot Savart's law calculates the vector magnetic field dP due to the interface length of the current. The total velocity field B can be found by integrating over the total length of all currents. As we can able to observe a figure in which the dB is known as the magnetic field and dl is the length and the theta is the angle between them and r is a vector where dB and overall the Biot-Savart law equation is dP bar equals to mu naught into I by 4 pi into dl into r square by r, where mu naught can be also written as 4 pi into 10 to the power of minus 7. And the total magnetic field. To find the total magnetic field, sum up the contribution of all current elements, where B bar equals to mu naught into I by 4 pi integral of ds into r by r square. The integral is over the intended current distribution. For example, B due to the current I in the state wires for a magnetic field near a large wire carrying the current I and should be the Biot-Savart law and gives the same magnetic field to the amperes, where B magnetic field B equals to mu naught into I by 2 pi into R. Magnetic field for a long straight conductor. Magnetic field for a long straight conductor. Find the magnetic field contributing from the small element of the current. Then integrate over the current distribution. The thin straight wire is carrying a constant current ds into r and dx into sin theta, where in the vector form. Integrating the overall current means gives the b equals to mu naught by 4 pi into I by a integral of theta 1 to theta 2 cos theta into d theta. Mu naught by 4 pi into I by a into sin theta 1 minus sin theta 2. This is the overall reaction. Magnetic field for a long straight conductor in specific case. If the conductor is in the infinite long and straight wire, where theta 1 can be written as half into pi and theta 2 can be written as half into minus half into pi, which is where b equals to mu naught by 2 pi into I by a. The magnetic field for a curved wire segment. Find the field at the point O due to the wire segment. Integrate the remembering that I and R are constants, where b equals to mu naught by 4 pi into I by a into theta, where theta is taken in the radians. Magnetic field for a circular loop. Magnetic field is for a circular loop of a wire. Consider the previous result. Magnetic field for a curved wire segments. Find the field at the point O due to the wire segment. Integrate the remembering that I and R are the constants, where b equals to mu naught by 4 pi into I by a. The theta is taken as the radians. Magnetic field for a circular loop of the wire. Consider the previous results, which is the full of circle, where theta is 2 pi r, where theta equals to 2 pi, and b can be written as mu naught by 4 pi into I by a into theta, where and also can be written in another form, theta by replacing there mu naught into I by 4 pi into 2 pi. By cancellation, we get the overall result mu naught into I by 2a. This is the field at the center of the loop. This is known as magnetic field for a circular loop of a wire. And the magnetic field of a circular current loop. The loop has a radius r and carries a steady state current I, and the finding the field at a point P. As you can able to observe that a figure in which and the magnetic field P at one point here in the x-axis, and the distance is taken and r is a resultant component vector, and current is passing through in the clockwise direction. And we can write all of the derivative form equation bx in x direction equals to mu naught into I into s by 2 into s square plus x square into 3 by 2. This is known as the magnetic field for a circular current loop. And comparison of the loops. Consider the field at a center of a current loop at a specific point x equals to 0. Then Px equals to mu naught I into a square by 2 into a square plus x square whole power 3 by 2, where a substitution x equals to mu naught into I by 2. According to previous equation, where Px equals to mu naught into I into a square by 2 into a square plus x square into 3 by 2, where x is in the comparison of the loops. In comparison of the loops, then we take that x equals to 0. By substituting the x equals to 0, we get mu naught into I by 2a. This is known as magnetic effect circular current loop. Leading to a formula, the x will become the 0. This is exactly the same beam as from the curved wire. And the magnetic field lines for the loops. In magnetic field of loops in magnet, we can able to observe that the magnetic field lines are south to north or north to south according to their directions. In the figure it shows that magnetic field lines surrounded from the current loop. Their current loop, in which current loop is known as some of the current entering into the loop equals to some of the current leaving out of the loops is known as the exact definition of the figure A. And figure B is known as compares the field lines to that of a bar magnet. Notice the similarities in the pattern. In figure A, the magnetic lines are in the circular and they are closed section, whereas in the figure B, the near to the magnet were closed section and remaining all they are away from their process. Note the similarity in the process pattern. And magnetic flux. The magnetic flux is associated with the magnetic field. It is defined in a way of similar to the electrical flux. Consider an area of an element dA of an arbitrary shaped surface. The magnetic field in these elements is P, and dA is a vector perpendicular to the surface and has a magnetic equal to the area dA. Magnetic flux phi B is known as magnetic flux. The unit of the magnetic flux is Weber. T into meter square equals to Weber. Phi B equals to integration of B into dA. This is the magnetic flux. Magnetic flux we can able to tell that phi equals to B into dA. Thank you.